Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Since we have completed chemical bonding, now we are going to start new chapter, that is states of matter. States of matter. It's a very important chapter for all competitive exams. In this chapter, we are going to learn about all the gas laws. Yes. Coming to states of matter. In this chapter, we are going to learn about all the gas laws. So first, we are going to start with this chapter, states of matter. So what is matter? Anything that occupies space and has mass is called matter. So anything that has mass and occupies space is called matter. So matter is anything that has certain mass and occupies some space. It is called matter. Matter is regarded as substance that has mass and volume. It has mass as well as volume. So matter is anything that has certain mass and occupies space, some space. So this is called matter. Next, different states of matter. We have solids, liquids, and gases. So in this chapter, we are going to learn about gases. In this chapter, we are going to learn about gases, that is solids, liquids, and gases. First, we have introduction about solids, liquids, and gases. Then we have more about gases in this chapter. Next, so physical states of matter. The physical properties of a substance depends on the state of existence of the substance. So how does a substance exist is nothing but it is called its physical property. It depends upon the physical properties of a substance, depends on the state of existence of the substance. Same compound, this point is important, you can just see here. Same compound has different physical properties in solid or liquid or gaseous states. So same substance, for example, iodine exists as solid as well as gas. It has different physical properties in gas as well as in solid, because in solid it has shape and in gas it has no shape in the form of vapor. So like that, same compound has different physical property in solid or liquid or gaseous state. The chemical properties of the substance do not depend on its physical state. The chemical properties of a substance do not depend on its physical state. And the physical state of matter depends on intermolecular. So mainly the physical state. How can we say it is solid or gas or liquid? It is based or depends upon intermolecular forces and effect of thermal energy. These are the two factors. One is intermolecular forces and second one is thermal energy. So based on these two factors only, the physical state of a substance exists. Next. So differences between three states of matter. What are the three states of matter? We have solids, liquids, and gases. First, solids have definite shape and definite volume, and liquids have no definite shape and assume the shape of the container. So it will take the shape of the container. It is not contained, it is the container. So here I'm rounding off, and it is nothing but a container. So liquids have no shape and assume the shape of the container, and gases neither have shape nor definite volume. So gases do not have shape as well as volume. Gases have no definite shape and volume. Next, in solids, the particles are arranged in ordered arrangement. Means it is in ordered management, like ordered arrangement of particles. So all the molecules will be aligned in an order like this, very close to each other. And in solids, the molecules are arranged in the form of ordered management, ordered arrangement of particles. In liquids, it is disordered clusters of particles, disordered clusters of particles. And extremely disordered particles are nothing but they have no order, and that is nothing but extremely disordered particles are nothing but gases. Solids have high density, they have intermediate density, that is not more high and not less also, and gases have very low density. Next, solids are incompressible, they cannot be compressed even by applying pressure, and liquids are slightly compressible even by applying pressure. So gases are highly compressible. Here we forgot to write here, gases are highly compressible, very important. By applying pressure, we can compress a gas to any level. Even you can see the same thing in cylinder also. So gases are highly compressible, liquids are slightly compressible, whereas solids are incompressible, not fluid. Because what are fluids? The substances which can flow are called as fluids. The substances which can flow are called fluids, and solid is not fluid and do not diffuse also. Whereas liquids are fluids, they diffuse to other liquids. Yes, they can flow. Whereas gases diffuse rapidly. They can diffuse rapidly. If you open a perfume bottle, the cork of if you open the cork of a perfume bottle, it will spread the whole room within a few seconds. Within few seconds, that's why we can say gases are fluids and they are diffusing rapidly. So all the gases diffuse very rapidly. Gases diffuse rapidly. Rapidly means very fast. I hope it is clear. So these are the general properties, physical differences between three states of matter. Next, more differences are also there, but based on this chapter, we are going to discuss only few topics. Next, intermolecular forces coming to. So the physical existence of a substance depends upon the two factors mainly. What are those? Intermolecular forces and thermal energy. So the intermolecular forces are the force of attraction or repulsion between the particles. So they are nothing but the forces of attraction or repulsion between the particles. These forces do not include any type of bonds like covalent bond or ionic bond, either by electrostatic force of attraction between ions or by sharing of electrons between the atoms, that is covalent bond. So these forces do not include any type of bonds, either by ionic bond or by covalent bond. So these are different than bonds. Attractive molecular forces are known as van der Waals forces, very, very important. So intermolecular forces mainly are either the force of attraction or repulsion between the particles. If they are nothing but consisting of forces of attraction, we will call them as van der Waals forces. What they are called? Van der Waals forces. I hope it is clear. So the intermolecular forces, attractive intermolecular forces are called as van der Waals forces. Next. So in types of van der Waals forces, we have dispersion forces or London forces. What are the different types of van der Waals? It's a very, very weak force. So by giving certain heat, it will become. So dispersion forces are London forces are induced dipole forces. So these are the three types of van der Waals forces. These are all called as attractive forces. Attractive forces are called as the attractive forces between the molecules, between the particles of a molecule are called as van der Waals forces. So these attractive forces, van der Waals forces are of three types mainly. Dispersion forces are London forces are induced dipole forces. Next dipole forces are next dipole induced dipole forces. So dipole induced dipole forces. So these are the three types of van der Waals forces we have. Next, dispersion forces. Next is what? Repulsion or dispersion force. These are the forces which exist between non-polar molecules and atoms. So dispersion forces are nothing but these are the forces which exist between, very, very important, non-polar molecules or atoms. What are non-polar molecules like? Oxygen molecule non-polar. Sharing of electrons between them is equal. Oxygen molecule, fluorine molecule, chlorine molecule, hydrogen molecule, chlorine molecule, bromine molecule, and so on. So all these are the non-polar molecules. Non-polar means equal sharing of electrons. Equal sharing of electrons. Polar means unequal sharing of electrons. So equal sharing of electrons. So these dispersion forces will be present in non-polar molecules or atoms. The non-polar molecules have symmetrical distribution of electron cloud and the dipole moment is zero. Very important. Dipole moment is mu. This we are discussing chemical bonding. Dipole moment mu is equal to E into D, where E is called charge and D is called distance between them. So dipole moment is equal to zero. So for non-polar molecules, these non-polar molecules have symmetrical distribution of electron cloud. Symmetrical means equal sharing and the dipole moment is zero. When two molecules approach each other, they become induced dipoles momentarily. So they become induced dipoles. Induced dipole means they become charged. Charged means partially charged. They becomes what? Partially charged. So when two molecules approach each other, they become induced dipoles momentarily. I hope it is clear. These are called dispersion forces. What are dispersion forces? These are the forces which exist between non-polar molecules or atoms. And non-polar molecules means like oxygen, fluorine, hydrogen, chlorine, etc. The non-polar molecules have symmetrical distribution of electron cloud, that is equal sharing of electrons, and the dipole moment is zero. Mu is equal to zero for them. So when two molecules approach each other, they become induced dipoles momentarily. How it takes place, I'll just show you now. So first, for example, atoms of atom A and atom B. You know, all the nucleus of the atom is charged with positive because they contain protons. This is also positive. So, atom symmetrical distribution of electron clouds, atom A and B. When these two are approaching each other, what happens? Atom A and atom B gets induced dipoles. Induced dipole means the slightly positive charge will move this side. So, due to which nothing but what happens is called induced dipoles. Induced dipoles. So these are strong. Next, dipole forces. First, we have complete dispersion forces. Next, we have dipole forces. These are stronger attraction forces among the intermolecular forces. So when compared to dispersion forces, these are stronger. And these are coming under attraction forces. They are also called as van der Waals force. So attractive forces in the molecules are nothing but van der Waals forces. There are three types. First is dispersion force or London force that we have already discussed. Next, we have dipole forces. So these are stronger attraction forces among the intermolecular forces. A dipole is a molecule having unequal distribution of electron cloud, very, very important, which is taking place in polar molecules. This we can take, this we can observe in polar molecules. Polar molecules like HCl. HCl is a polar covalent bond where we have unequal sharing of electrons. So a dipole is a molecule having unequal distribution of electron cloud, which results in a positive and negative centers in the molecule. So it results in a positive and negative center in the molecule. In the previous dispersion force, we have seen only positive center in the molecule, and here we'll see positive as well as negative center because they become partially charged. So the positive end attracts the negative end of the other molecule. Very, very important. The positive end attracts the negative end of the other molecule. So this is called dipole forces, and it is observed in polar molecules like HCl, where they have unequal distribution of electron clouds. Due to high electron affinity of chlorine, it will pull the shared electron towards itself, due to which what happens, hydrogen develops partial positive charge and chlorine develops partial negative charge. So this is called dipole induced dipole force, and it is more stronger force than the dispersion force or London force or induced dipole force. So this is called dipole forces are stronger attraction forces among the intermolecular forces. So I hope it is clear. Next. So they'll have positive and negative end. The negative end will be attracting towards positive end of the other molecule or other atom. So this is called dipole attraction. So this is called dipole attraction, and these are stronger than London forces or dispersion forces. Next. Next, dipole-induced dipole forces. So this type of intermolecular forces existing between a polar molecule and a non-polar molecule. So here, as I told you, so this type of forces existing between a polar molecule means the charge of polar molecule will go to a non-polar molecule. So the permanent dipole will induce the polarity in the non-polar molecule. So because of the polar molecule, it will induce the charge on the non-polar molecule. So the magnitude of attraction force is in between to that of London forces and dipole forces. Means is the order will be dipole first dipole greater than uh, this one, dipole induced dipole, which is far greater than London forces, that is dispersion forces. London force are dispersion force. This is the order of polarity. So the attraction forces. So the magnitude of attraction forces is in between that of London forces and dipole. So which is stronger among all the van der Waals forces is dipole force. Next stronger is dipole induced dipole. So due to the dipole moment present in polar molecule, it will give the polarity to non-polar molecule also. So due to which it is called as polar molecule and non-polar molecule combination. They will form dipole and induced dipole forces. I hope it is clear now. Next. So first dipole, it is a polar molecule and a non-polar molecule which is having positive charge. in the nucleus will be coming closer to each other, due to which what happens, it will induce the charge opposite to the non-polar molecule, that is induced dipole. So it also becomes positive and negative, positive and negative, positive and negative. Anyway, this is positive and negative dipole, due to which non-polar molecule also gets induced dipole, due to which it also becomes positive and negative. So this is called the attraction force, and this is nothing but van der Waals attraction force of type 3. Next, very small here, next force is hydrogen bonding. So already you know hydrogen bonding, we have discussed in chemical bonding. So what is hydrogen bond? It is a special case of dipole forces. Hydrogen bond is a special case of dipole forces, which is very stronger. This is found in the compounds where hydrogen is bonded to the high electron atoms like fluorine, oxygen, and nitrogen. For example, hydrogen fluoride is a molecule. It is bonded with the, this fluorine is in bonding with the another hydrogen, or you can say, so hydrogen is bonding with fluorine. So even you can write like this also. For example, in case of water also you'll observe this. Water, we have oxygen, hydrogen, and hydrogen. This hydrogen is in bonding with again one more oxygen and hydrogen and hydrogen. So this is called hydrogen bonding. This is called what? Hydrogen bonding. It is represented by little dots. This we have already discussed in, this we have already discussed in chemical bonding. So it is a special type of, is a special case of dipole forces. That's why hydrogen bonding is stronger. And due to the presence of hydrogen bond, the molecule is more rigid and the boiling point or melting point increases. Boiling point of the molecule, also melting point of the molecule increases due to hydrogen bonding. So the example, that's why water, the boiling point of water, even though water is a liquid, the boiling point is 100 degrees C because of hydrogen bonding. So hydrogen bond is a special case of dipole forces. So we have, based on the physical substance, we have attractive forces as well as repulsion forces. In attractive forces, we have van der Waals. Attractive forces are nothing but van der Waals forces. It is of three types. First is London force or dispersion force. Second is in dipole force, which is very stronger like hydrogen bond, and third one is dipole induced dipole. So all these 3 points are important. So I hope it is clear. Next, so second factor is attractive force, intermolecular force, as well as thermal energy. So effect of thermal energy of physical states of matter. So thermal energy is the energy arising due to the movement of atoms or molecules. Thermal energy is directly proportional to the temperature. So it is directly proportional to the temperature of the substance. If the intermolecular forces are very less, the molecules or atoms do not attract each other, and hence they cannot form solids or liquids. So if the intermolecular forces are very, very less, like in case of gas, I told you it is very negligible. Negligible in the sense there is no intermolecular force in a gas because the molecules are very far apart. So if the intermolecular forces are very less, the molecules or atoms do not attract each other, hence they cannot form solids or liquids. So this is nothing but thermal energy. So mainly thermal energy depends upon, thermal energy is energy arising due to the movement of atoms or molecules. It is directly proportional. It is directly proportional to the temperature of the substance. Next, if the intermolecular forces are strong, then the substance can exist in the form of solids or liquids, as we already know. Now, gas, liquid, solid. So predominance of intermolecular forces. So as the intermolecular force increases, it changes to gas, changes to liquid, liquid changes to solid. So first, there is no intermolecular force of attraction in gas. So in gas, what happens? The intermolecular forces is negligible. Intermolecular forces, intermolecular forces are negligible. Negligible means very, very less. No need to count that also. Next, in liquids, they have moderate. The intermolecular force of attraction are moderate. In solids, it is very strong. So the intermolecular forces are strong in solids. They are very close to each other. So if the intermolecular forces are strong, then substance can exist in the form of solids or liquids. So gas, liquid, solid. Predominance of intermolecular forces goes like this. And solid, liquids, and gas, predominance of thermal energy goes like this. Thermal energy increases opposite. Exactly, it is opposite, because if you heat a solid, slowly it changes to liquid. and still if you heat further, it changes to gas. So that's the predominance of thermal energy. For example, if we take ice, ice is a solid. Ice changes to water at 0 degrees C. If you increase the temperature, ice changes to water. So water changes to at 100 degrees C, it changes to water vapor. So this is nothing but water vapor or steam. You can say water vapor or steam. So this is solid, this is liquid, and this is gas. Solid, liquid, and gas. Solid, liquid, and gas. So solid, liquid, and gas, predominance of thermal energy goes like this. So in gas, the thermal energy is more. Because of thermal energy only, the gas molecules will be formed. Means because when you give heat to when you heat a substance like solid, it changes to liquid and then it changes to gas. So this is the scenario. I hope you understood clearly. Next. Gaseous state, general characteristics. Now, in this chapter, we are going to learn about more about gases, not about solids or liquids. In solids, we'll study based on solids in the second year, that is 12th class, where we have solid state chapter. Now, in this class, in this lesson, we'll study about mainly gases and few points about liquids. So, gases are highly compressible and expandable. There is no limit for its expansion. It can go to any level. So gases exert pressure equally in all directions. Very, very important. Gases exert pressure. So they exert pressure because they move randomly in all the directions, due to which what happens due to the movement of molecules, they exert pressure equally in all the directions. Gases have much lower densities than solids and liquids. They have very, very low density. The gas molecules are very free to move around, and gases do not possess any definite shape, size, or volume, as we already know. Gases mix evenly and completely in all proportions. So that is called gases mixes evenly. Evenly means easily, and proportionally in all the proportions. Evenly and completely in all proportions. Next, measurable properties of gas. Based on this only, we have gas laws. First, we can measure the mass of the gas, pressure of the gas, volume of the gas, temperature, and its density. So all is nothing but gas laws only. So what are the measurable properties of gas? Mass of the gas, pressure of the gas, volume of the gas, temperature of the gas, and density. So we can measure the mass of the gas. Now, what is the mass of a gas? Mass of the gas is expressed in terms of moles. In chemistry, we know this is the mole concept. So mass of gas is measured in moles, and 1 mole of a gas nothing but occupies 22.4 liters at STP. 1 mole of a gas at STP occupies 22.4 liters. So number of moles. So number of moles of a gas is equal to mass of the gas by molar mass of the gas. For example, 0.5 moles of carbon dioxide. Suppose if we take 0.5 moles of carbon dioxide gas, so it is nothing but what? 0.5 means how much we have to take? Mass of the gas is equal to, so now how to find mass of the gas? So mass of carbon dioxide is equal to, mass is equal to number of moles into molar mass. Number of moles into molar mass. So mass of the carbon dioxide is equal to mass of 0.5 moles of carbon dioxide gas is equal to number of moles, it is equal to 0.5 into molar mass of carbon dioxide 44. So 0.5 into 44 is 22 grams. So 1 mole of carbon dioxide can contains 44 grams. 0.5 moles contains 22 grams. Like that we can find number of moles, or we can find from the mass of the gas we can find number of moles. So for example, next in the same question they can ask you, how many moles does how many moles how many moles are present in 64 grams of oxygen gas. So how many moles are present in 64 grams of oxygen gas means given weight is 64, oxygen weight is, so we can take it as number of moles is equal to, I'm writing the answer here since we don't have place. So number of moles of oxygen is equal to 64, given weight is 64 grams. So I'm writing here 64 divided by 32. So 32 ones are 32 twos are. So answer is 2. So in this way you can find number of moles. So mass of the gas is expressed in terms of moles, and number of moles is equal to mass of the gas by molar mass of the gas. Molar mass of oxygen is 32 grams. So I hope it is clear. So this is the first measurable property of the gas, that is called mass of the gas. Next we have volume of gases. So already we know volume of gas is expressed in terms of liters. Spelling is wrong here. I'm correcting it. Liters. Liters or cubic meters or cubic centimeter, and the relation is 1 liter. This relation is important. 1 liter is equal to 1 decimeter cube, which is also can be equal to 1000 cc or 10 to the power of minus 3 meter cube, or 1000 ml. Cc, cubic centimeter, or milliliter, both are same. Cubic centimeters is equal to milliliters, ml. So 1 liter is equal to 1000 ml or 1 decimeter cube or 10 to the power of minus 3 meter cube. So this is the volume. So volume of a gas is expressed in liters. I hope it is clear. Next, pressure, the force of attraction. So the pressure of a gas is force exerted by the gas on a unit surface area. That's why we'll call pressure is equal to force by area. Pressure is equal to what? Force by area. What is the force? Force exerted by the gas on a unit surface area is called pressure. So pressure is equal to force by area. The SI unit of pressure is Pascal. The most common units to express pressure, atmospheres, 1 atmosphere, and it is nothing but 760 mm of mercury, and it is equal to 1.013 10 to the power of 5 pascals, which is also equal to 0.98 bars. You can express the pressure in terms of bars also. So these are the main units of pressure. So this interconversions of matter is very, very important. So 1 atmosphere is equal to 760 mm of mercury or 76 centimeters of mercury. Both are same. This value we got it from barometer experiment, atmospheric pressure, barometer experiment. So 1 atmosphere is equal to 760 mm of Hg or 76 centimeters of mercury, or it is also can be written as 760 TORS. Some more units of pressure. 70 tar, 1 tar. See, 1 tar is equal to 1 mm or 1 by 10 centimeters. So 760 mm, I mean 760 tars or 76 centimeters, which is equal to 1.013 10 to the power 5 pascals, which also can be equal to 0.98 bars, bar. So these are the various units of pressure. The most common units used to express pressure are nothing but atmosphere, millimeters of mercury, and Pascal, as well as TOS and bars. So these are the most common units of pressures. I hope it is clear. Next measurable property, temperature and density. So the degree of hotness or coldness of a body is called its temperature. The degree of hotness or coldness of a body. The degree of hotness or coldness of a body is called its temperature. So this is the definition of temperature. The degree of hotness or coldness of a body is called its temperature. Temperature of a gas is measured in kelvins or degrees Celsius. So it is measured in kelvins or degrees Celsius. You already know 0 degrees C is equal to 273 kelvins. So this is a relation between degrees C and kelvins, and 1 degree C is nothing but just 274 kelvins and so on. So the rise of temperature in degrees C as well as Kelvin is same. Rise of temperature is same. Is same in both degrees and kelvins. So density of a gas is measured in terms of grams per liter or grams per cc. G per cc or grams per liter, cubic centimeter or grams per liter, kilograms per kg per meter cube, grams per centimeter cube. We can call it as grams per centimeter cube or kg per meter cube. This is the unit of density. Density is nothing but density is equal to mass by volume. Mass by volume. Mass is expressed in grams, volume is expressed in centimeter cube. If mass is expressed in kgs, then volume will be expressed in meter cube. So these are the units of density. So gases have density, mass, pressure, temperature, and volume also. These are all the parameters of gases. That is measurable properties of gases are nothing but we have what are the measurable properties of gases. So we have already discussed, that is mass. First one we have mass. Second one we have pressure. Third we have volume. So units also we have discussed. And fourth we have temperature. Fourth we have temperature. And fifth we have density. So these are all the parameters, measurable parameters of a gas or measurable properties of a gas. I hope it is clear. Next, we are going to discuss about this only. And based on this only, we have gas laws. So now we are going to discuss gas laws. Yes. Now we are going to discuss about gas laws. So the relation between these measurable properties are nothing but gas laws. What are gas laws? The relation between the measurable properties of the gases are nothing but gas laws. Simple, it is very simple. So what are gas laws? The properties of gases are governed by certain laws known as gas laws. So the relation between the measurable properties, the relation simple in simple words, what you'll say, the relation between the measurable properties of a gas, the relation between the measurable properties of a gas. Measurable properties means what we already know, that is density, temperature, mass, etc. Measurable properties of the gas are nothing but gas laws. They are nothing but what? Gas laws. So we have, what are the gas laws? We have Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, and Dalton's law of partial pressures. So all these are the gas laws. Now we are going to discuss about all these gas laws only. So very, very important. Boyle's law, Charles' law, Charles' law, Gay-Lussac's law, Avogadro's law, and Dalton's law of partial pressures. So in this, what type of questions you'll get in the examination also we'll discuss. So first coming to Boyle's law. Yes. So what is Boyle's law? This law states that at constant temperature, here the conditions are important, graphs are important, that constant temperature, the volume of a gas, given mass of a gas is inversely proportional to its pressure. Means what? As the volume increases, pressure decreases. As the pressure increases, volume increases. So P is directly proportional to 1 by V, or P is equal to K into 1 by V, that is called constant. For removing proportionality, we had to use constant. So K into 1 by V. So PV is equal to constant. So what is this? PV is equal to constant. But as we can write P1 V1 is equal to P2 V2, or P1 by P2 is equal to P2 by V1. So these are the formulas from Boyle's law. These are the formulas from Boyle's law. Very simple. At constant temperature, this law you have even learned in class 10th or 9th or 8th in school level. So, but at constant temperature, the volume of a given mass of a gas is inversely proportional to its pressure. And this law will study differently in this session. So you can understand more about clearly. So now we are going to discuss more about this Boyle's law. So effect of pressure on the volume of 0.05, 0.09 moles of carbonized gas at STP, that is 300 kelvins. So what is the effect of pressure on the volume of 0.09 moles of carbonized gas? So effect of pressure on the volume of 0.09 moles of carbonized gas at STP, at 300 kelvins. So when the pressure is around 10 to the power of 4 pascals, 10 to the power of 4 pascals, the volume is the volume occupied by 0.09 moles of carbonized gas is 2. So volume is 1.1112 and 1 by V. PV is equal to 22.40. So simply 2.5. What is this? This is the pascals. 2.5, 89.2. Like this we have effect of pascals. 10 into 10 to the power of 4, that is equal to 10.5. That is nothing but 1 atmosphere. So at atmospheric pressure, the volume of gas occupies 22.4 liters and 44.6 is 1 by V and 22.40. This graph is just only an observation. So already we know 1 mole of any gas occupies 22.4 liters STP. So I'm writing here 1 mole of any gas occupies 22.4 liters at STP. STP means standard temperature and pressure. That is, temperature is 273, but here the temperature is 300 kelvins. So here, what is the effect of pressure? As the pressure is increasing, volume is decreasing. You can see here 2, 112, 2.5, 89.2, 3.5, 64.2. So it is further decreasing. Here pressure is increasing from 2 to 2.5. Volume is decreasing from 112 to 89.2 meter cube. Similarly, pressure is increasing from 2.5 to 3.5. Volume is decreasing from 89.2 to 64.2. Like this, when pressure is up to 10, it is becoming 22.4. So I hope it is clear. As the pressure increases, by this what you can say, as the pressure increases, volume decreases. You can just see here. And 1 by V value also increases. 1 by V value means 1 by V means because P is proportional to 1 by V. So 1 by V value increases. You can just see here. So 1 by V value increases as the pressure increases from down to. So you can see here 1 by V value also increases. For 2 it is 8.90, for 2.5 it is 11.2, for 3.5 it is 15.6. So as the pressure increases, 1 by V value also, 1 by V means 1 by volume also increases, and PV becomes constant, 22.40, 22.3, PV by P, it is decreasing again. You can just see. So I hope it is clear. So this is the graphical representation of Boyle's law. Now we are going to see graphical representation of Boyle's law. Very, very important. They'll ask these graphs, very, very important. These graphs are very important in the examination. They'll ask either the graphs or the relation between the temperatures, either this relation and this relation they'll ask. So these two graphs are important. Either they'll ask the graphs or the relation. So here, if you plot a graph between P and V, taking pressure on y-axis and volume on x-axis, as the volume increases, you can see here, as the volume increases, pressure decreases. This forms a curve. So as the volume increases, you can see here, and pressure decreases. So the pressure is decreasing like this. They form curves. And what about the temperature? Here, this relation is most important. How it came, I'll just explain you. So what is this relation? At temperature T1, at low temperature, what happens? Volume increases. So the pressure decreasing, the decrease of pressure is more at temperature, less temperature, and the decrease of pressure is little bit less at high temperature, and the decrease of pressure is still less at very high temperature. So we can say by this, we can say pressure is proportional to temperature based on Gay-Lussac's law. So as the temperature is low, pressure is very, very low. As the temperature is high, pressure is very high, high. That is based on, this law is based upon a constant volume. We can say it is Gay-Lussac's law. Gay-Lussac's law, which we are going to discuss in the next coming session. So what do you understand by this? At very low temperature, means since T1 is less when compared to T3 and T2 and T1, the decrease of pressure is more and the increase of volume is more. Sudden decrease of pressure takes place. See here, if we take the pressure here, for example, 10, so you'll get it here exactly 6, say for example 10, 8, 6, 4, 2, 1, sorry, 2, and here it becomes 1, for example. So the pressure is decreasing from 10 to 1. When you take pressure here up to here, so it will decrease up to, at high temperature, to decrease up to 2. At very high temperature, it is decreasing up to 4. So it means the decrease of pressure is less at high temperature. What you can understand, the decrease of pressure is less at high temperature. Anyway, volume will increase. Whenever the pressure decreases, volume increases. That you can see in the diagram. But so the decrease of pressure is less at high temperature and the decrease of pressure is more at low temperature. This is due to Gay-Lussac's law. What is this Gay-Lussac's law? So based on Gay-Lussac's law, we have pressure is proportional to temperature. The same thing happens here. So if we take P into 1 by V, it is a straight line. It is a straight line, and very high temperature, the pressure is more. So you can see at high temperature, the pressure is more when compared to T2 and compared to T1. Slight difference. So this is the relation. They'll ask in the exam this relation only. If you plot a graph between P and 1 by V, it is straight line, increasing line, because P is proportional to 1 by V. Since P is proportional to 1 by V, we'll get a straight line. And since P is inversely proportional to V, we'll get inclined line like this. So I hope it is clear. So this graph is very, very important. From this graph only they'll ask examination. How they'll ask the question in the examination? They'll give the graph, they'll give T1, T2, T3 like this only, and they ask us which of the following relations is correct regarding the above graph. They'll give you first option T1 less than T2 less than T3, T1 is equal to T2 is equal to T3. Like this, they'll change the four options, and in that the option is T3 greater than T2 greater than T1. The important point is, as at high temperature, the decrease of pressure is less. The decrease of pressure is less at high temperature when compared to the decrease of pressure is more at low temperature. You can I'll write the statement. The decrease of pressure is less. The decrease of pressure is less at high temperature, and it is more. The decrease of pressure is more. The decrease, I'm writing down whatever, decrease of pressure is more at a low temperature. These 2 points you have to note down, please. All of you note down in your classwork when you're seeing this graph. So the decrease of pressure is more at low temperature, and the decrease of pressure is less at high temperature. And the increase of volume is also based on temperature. The increase of volume is nothing but it is directly, since here we are taking volume constant, constant volume, same increasing. So we can say it is volume is constant. So at constant volume, since volume is constant, here also volume is constant, so the increase of pressure and 1 by V value takes place like this. So these two graphs are most important, very, very important. Please note down these graphs, and these relations, especially particularly these two relations, are important for these graphs. So what is the relation? The decrease of pressure is less at high temperature, and the decrease of pressure is more at low temperature. That is based on Gay-Lussac's law. Is as pressure is proportional to temperature, high temperature, high pressure, low temperature, low pressure. So I hope it is clear. Next, some more graphs based on log P versus log P. If you take log P versus log P, it is a decreasing slope where T3 is greater than T2 is greater than T1. And this graph is also important. And if we take PV versus V, it is a constant, because PV versus V, PV is equal to constant. So volume is constant at temperature T1, T2, and T3, where the temperature is T3 is greater than T2 is greater than T1. So all these four graphs are very, very important. They will ask graphical representation, either numerical from Boyle's law or graphical based question. If they ask graphical based question, they'll give either of these four graphs which I have shown you in the some PPTs. And the relation is also very, very important. That is temperature relation. I hope it is clear. So the one which is here, one more important thing we have to observe, the one which is constant, that only we have to relate. Because in Boyle's law, we already know at constant temperature, the dependence of pressure and volume. So relation between pressure and volume is what? So and that constant temperature, we are going to get the relation. Similarly, for other laws also we'll see. Always the constant parameter will be giving you the relation. So log P versus log P, if you plot a graph, it will be decreasing slope like this. Because as the pressure decreases, volume also decreases. If you take PV versus V, it is a straight line parallel to x-axis because it is constant. Because PV is equal, since PV is equal to constant, we will get the graph like this. Since PV is equal to constant, we will get the graph PV is equal to K. I hope it is clear now. Next. Next, Charles law. This law states that at constant pressure, here very important. So we are going to find a relation between constant pressure in the graphs. So at constant pressure of the gas, the volume of a given mass of a gas is directly proportional to its absolute temperature. So always absolute temperature means it is measured in kelvins, not in degrees C. So even if they are given in degrees C, also we have to change the temperature into kelvins. Very, very important point. So whenever they give a numerical based on Charles' law in the gaseous and states of matter questions in this chapter. Whenever they are given the temperature, always you have to change the temperature into kelvins. Even though the question is in degrees C, answer is also in degrees C, but still you need to change the temperature into kelvins, because based on Charles' law, it is not directly depending on the temperature. At constant pressure, the volume of a given mass of a gas is directly proportional to the absolute temperature. That is nothing but Kelvin temperature. Very, very important. This absolute temperature word is different, not this normal temperature. It is denoted by capital T. Normal temperature denoted by small t, but absolute temperature denoted by capital T. So always you have to change the given mass of a gas. You have to change the temperature in the temperature is given in degrees C. We have to change them into kelvins. That is most important point. So V is proportional to T, or V is equal to KT, or V by T is equal to constant. We can say V1 by T1 is equal to V2 by T2. These are the formulas we have. So V1 by T1 is equal to V2 by T2. So at constant pressure, the volume of a given mass of a gas is directly proportional to absolute temperature. I hope it is clear. Next. So we'll see the same graphs in Charles law also. Kelvin scale of temperature. Charles law gave a new scale of temperature known as Kelvin scale. Since I told you absolute temperature is based on Kelvin scale, where T is temperature in degrees centigrade. So Vt, the new temperature, new volume at temperature T is equal to V naught, initial volume, plus T by 273.15. Because how we got this 273.15? Because 0 degrees C is equal to 273.15 Kelvins, very, very low temperature. 273.15 degrees C. So into V naught, initial temperature. This is the relation. Vt is equal to V naught into 273.15 plus T by 273.15. Charles' law can also be stated as pressure remaining constant. The pressure remaining constant, the volume of a given mass of a gas increases or decreases by 1 by 273.15 of its volume at 0 degrees C for energy for everyone. So for 1 degree centigrade, rise or fall of temperature. 1 degree centigrade, rise or fall of temperature. So volume of a given mass of a gas increases or decreases by 1 by 273.15 of its volume at 0 degrees C. And for every 1 degree C, for every, here it is not energy, for every 1 degree rise of temperature, every 1 degree centigrade rise or fall in temperature. So I hope it is clear. So very, very simple in application of questions. Next, the temperature in degrees Celsius is converted into Kelvin square by T is equal to 273.15 plus T. So Vt is equal to V naught in T by 273, where T is the temperature in degrees Celsius. And for this, we'll take in conversion 0 degrees is 273 Kelvins only, not 273.15. Actually, it is exact value is 273.15. For numerical sake, we'll take that 1.15 is neglected. So the degree centigrade are rising fall of temperature. So next, graphical representation. If we see with respect to temperature, it is minus 273 degrees C, because minus 273 degrees C is equal to absolute temperature. Absolute temperature is 0 kelvins. What is absolute temperature? I'll write here. 0 kelvins is called absolute temperature. So 0 kelvins is equal to minus 273.15 degrees C. Exactly minus 273.15 degrees C. So that's why the gas is 0 kelvins here. This is called what? 0 kelvins. 0. So 0 Kelvin is called minus 273.15 degrees C. So minus 273. So volume is proportional to temperature. As the volume temperature increases, volume also increases. And for 1 mole of a gas, it is 22.4 liters. So it is 0 degrees C temperature. I hope it is clear. At 273 kelvins or 0 degrees C. At STP means what? 0 degrees C. STP means 0 degrees C. Volume is equal to 22.4 liters. So I hope it is clear. Next, if we take volume with respect to temperature, it is the graph will be like this: P1, P2, P3, and P4. As I told you, the constant ones only we have to take into consideration. The relation, this relation they will ask in examination. And the graph is a straight line, nothing but simple. It is an increasing graph. As the temperature increases, volume also increases. And these are the different pressures: P1, P2, P3, and P4. So more rise in volume will be taking place at low pressure because of Boyle's law. Since V is proportional to 1 by P, so at low pressure, volume increasing is more. If you take the volume values, you can see here the volume values, it is more in case of P1. Next, it is less in case of P2, less in case of P3, and less in case of P4. So at high pressure, volume is increase of volume is low. At high pressure, increase of volume is low, and at low pressure, volume is increasing high. So That is based on Boyle's. That's why the relation we got it as P1 is less than P2 is less than P3 is less than P4. So pressure P1 is less than P2, P3, and P4. So at high pressure, volume is increase of volume is less. Increase of volume is low because of Boyle's law. And at low pressure, that is less pressure, that is P1, increase of volume is high. Increase of volume is high. So these points are important. Please note down. So whenever they give a graph between like this, volume and temperature, and they give P1, P2, P3, P4, if the temperature decreases, if they can give the temperature in kelvins also. Kelvins means directly temperature they'll give in kelvins. Then straight line from origin only we can take. We can take from origin. So I hope it is clear. That graph also I think I'll show you now. Next, we have Gay-Lussac's law. So after Charles' law, we have Gay-Lussac's law. This law states that at constant volume, the pressure of the given mass of a gas is directly proportional to absolute temperature. And I told you P is proportional to absolute temperature at constant volume. By combining these three laws, we have gas equation also. So at constant volume, the pressure of the given mass of a gas is directly proportional to absolute temperature. So P is proportional to T, P is equal to K into T, P by T is equal to K. P1 by T1 is equal to P2 by T2. So I hope it is clear. So this law we have discussed in Boyle's law only. So graphical representation at V1, V2, V3, different volumes. Because volume is constant here, so we are going to find a relation between volumes. That's why I told you, whichever the term is constant, they'll definitely ask in the examination the relation between those constant terms. So pressure is increasing, the temperature, as the temperature increases, the Kelvin temperature, this is called Kelvin temperature. So 0, 100, 200, 300, 400. So it is starting from origin. So as the temperature increases, pressure also increases, and high pressure will be there at low volume, and low pressure, increase of pressure is less in case of high volume. So at high volume, pressure is low, just like Boyle's law. So I hope it is clear. So that sentence also I'll write if possible. So high increase in pressure value takes place at low volume. So that's why V1 is less. And decrease in pressure takes place at high volume, that is V4. More volume V4. So it is at V4. So this is at V1. So low pressure, high pressure. I hope it is clear. Next. So this relation they'll definitely ask in the examination, graphical representation. Next, combined gas equation. So we know from Boyle's law, V is proportional to 1 by P, and from Charles' law, we have V is proportional to T, and from for 1 mole of a gas, K is equal to. So we can, by combining these two laws, we can say V is proportional to T by P, and for removing proportional, we had to use constant K is equal to, that K is called universal, that is universal gas constant. For 1 mole of a gas, K is equal to universal gas constant R. So PV is equal to RT. So for N moles of the gas, PV is equal to nRT. So this is called ideal gas equation. Ideal gas equation, PV is equal to nRT, or you can write P is equal to PV is equal to, since N is equal to weight by molecular weight into R into T. So the same formula you can write like this also. So this is called ideal gas equation. By combining Boyle's law and Charles' law, we get ideal gas equation. This is called Boyle's law as well as Charles' law. By combining these two, V is proportional to T by P. And for removing proportional, we have to use constant. So V is equal to RT by P for 1 mole of a gas. So by this we can say PV is equal to RT, or PV is equal to nRT. So I hope it is clear. Very simple to understand gas equation, but numericals are very most important. Very important is values of universal gas constant. The value of R depends on pressure, volume, temperature, and number of moles, because already we know from ideal gas equation, PV is equal to nRT, implies R is equal to PV by NT. So P into volume by N into T. So that is called R. So the value of R is 8.314. When you take joules per Kelvin per mole, it is equal to 1.987 or equal to 2. It is almost equal to 2. When it is calories per Kelvin per mole, R value is usually you use this value when you take pressure, that is volume pressure. So liter, atmosphere, temperature, and moles. Total four, all the four values we have got it here. So R is equal to 0.0821. Liter, atmosphere, Kelvin inverse, mole inverse. Similarly, R is equal to 0.083 liters bars. Simple it is. Just if you take the pressure in terms of bars, Kelvin inverse is temperature and moles is number of moles. So based on these four values, only R value. Usually use this value in almost all the cases. And when the energy, we are calculating energy with respect to kinetic energy and all. If the energy is given in calories, we have to use this value. If the energy is given in joules, we have to use this value. So I hope it is clear. So these two we'll use in terms of calculating kinetic energy of the gas molecules. Kinetic energy of gas molecules. When you are calculating kinetic energy of gas molecules, we'll use these two values. I hope it is clear. And when you are calculating normal gas constant value, we'll use these values. Next. So SI unit of R is equal to Newton per meter square. It is when pressure is 101.325 pascals or Newton per meter square. Volume is equal to 0.0224 and T is equal to 273 and N is equal to 1. Its value is 8.314. It's very simple by substituting these values. How we got these values also, we have shown it. Next, we have Boltzmann constant. It is a ratio of universal gas constant and the Avogadro number. So if you take K is equal to R by N, where R is called 8.314, that is universal gas constant divided by number of molecules. So for 1 mole of any gas, it contains Avogadro number of molecules. So 6.022 in 10 to the power 23, its value is equal to 1.38 in 10 to the power minus 23 joules per Kelvin per molecule. Joules per Kelvin per mole, and this is nothing but joules per Kelvin per molecule. So that is the difference between R and K. So R is nothing but it is per mole, joules per Kelvin per mole. That is based on R value. Whereas K value, that is Boltzmann constant, is nothing but joules per Kelvin per molecule. Very, very important here. It is nothing but molecule. So each and every molecule. So I hope it is clear. These values are very important. They will not give these values in the examination. We have to remember these values. So we have discussed about up to ideal gas equation. In the next class, we'll discuss more about, in the next class, we are going to discuss more about numericals of gas laws, and then we'll discuss new topic. I hope it is clear. So today we have discussed all the gas laws and what are the measurable properties of gases and what are the types of force existing in gas. So I'm stop sharing now. So I hope it is clear. So we are ending this class. Thank you all.